I want to take one more lecture on dielectric materials, even though I thought I would just stop with dielectrics in the previous material. But given that I have enough time to do this, I will take one more lecture to talk about actual dielectric materials, the types of capacitors, and advanced dielectrics, what are called high-K dielectrics that are used in semiconductor technology. So this will cover a little more in detail things we may have touched upon in the earlier lecture. And so we will do that today, mainly focusing on the materials aspects of dielectrics. Not so much mechanisms and things like that, but design and so on. Let me begin by asking the question for capacitor materials. How do we decide what materials to choose for the particular application? And there are different requirements that we have. One would be what capacitance value we are looking for. With certain kinds of designs and materials, it is not possible to get in a certain reasonable size enough of capacitance. So we'll have to make our choice depending on what capacitance value we are looking for. What's the frequency of the application? We've seen a frequency dependence for polarization and hence for capacitance. So frequency of application will be very important. It's typically seen that if you're talking of low frequencies, you can have higher capacitance values. Okay? That's possible when you're working with low frequencies. And when we come to high frequencies, typically lower capacitance values are achievable. The third thing is we know that there are losses in a capacitor. What is the minimum, what is the maximum tolerable loss? All right? For a given application, how much loss can we tolerate before that is useless? The fourth thing would be the maximum working voltage. This is related to the idea of dielectric breakdown. We know that we cannot go on increasing the field that is applied across the capacitor without ultimately causing breakdown, and therefore we have to know what is the maximum working voltage that this particular device will see. And two other things that are related more to the economics of it, one is size and one is cost. These are the practical side of it. What size can we, I could probably achieve capacitance by making it very large, the one that I want, but if I'm trying to put it inside something which has got a very small size, the whole package itself is so small, I'll have to find a capacitor that can give me that value to fit within the package. It's a real practical dilemma. Cost is the other thing. I may have options, which is the cheaper option of the two. So when we talk of capacitors, high voltage capacitor requirements, what are called power capacitors, will have very different requirements than, say, capacitors used in ICs or in our chips, as we call them. IC, integrated circuit, right? These have got very small voltages applied across them and so on, and the values that are required are very different than what capacitors may be used in high voltage circuitry. So the requirements will be very different. Let me sketch out a couple of charts that will give us some idea of the kind of materials, the range that is used, and over what ranges we can talk about. What I'm going to do is simply sort of like a bar graph. We're talking of capacitances, 1 picofarad, 1 nanofarad. Roughly, it's just a range micro, that's 1,000 microfarads, and 10 to the power 4 microfarads. That's the kind of range over which we are looking. What kind of capacitors or what kind of materials and designs would satisfy this requirement in terms of the achievable capacitance? When we look at it for using paper and plastic film, we can achieve somewhere from few picofarads to microfarad range. Paper, plastic films, you can do that. And if we look at mica, which is well known as a dielectric, it's an insulator, somewhat in the lower capacitance range, we have mica. And then there are ceramics that can be used, single layer ceramics. We'll see what the definitions and ideas involved here are between single layer and multi-layer and so on. Single layered ceramic capacitors will be of a more limited range. Multi-layer allows us to extend it a little further. Again, ceramic capacitors, but multi-layer capacitors. If you want even more higher capacitances, then what we have to do is to go in for the electrolytic capacitors. This is the solid electrolyte. Solid electrolyte, say based on aluminum or tantalum. And then to still even higher capacitances, we can go using the liquid-filled electrolytic capacitors, again based on aluminum or tantalum or something like that. But there's a liquid, and that will give you the highest capacitances. So depending on the range of capacitances that you're interested in, you would make your choice of the material and design that is involved. Is it too small for you to read? You can read? Otherwise, I can read it out a little bit more. Okay. So this is what we have as far as the electrolytic, the range of capacitances and the types of materials that are used. I'm going to sketch almost the same thing again, except in terms of frequencies. What frequency of operation can we use these things to? Okay. If I'm too fast, I can slow down, or you can take this from me after class. In the interest of time, I'm not holding on to this for very long. But it just shows you the different types of materials, and we'll take them up in detail. I'm going to sketch again in terms of frequency. The whole thing is now in terms of frequency. 1 hertz, 1 kilohertz, 1 megahertz, 1 gigahertz. In the lowest frequency range, we have the tantalum electrolyte cell, electrolytic capacitor. Slightly higher frequencies with aluminum electrolyte. Now remember, the different mechanisms, polarization mechanisms that we studied are responsible. How does this material function as a capacitor? How are the dipoles created? How is charge stored? That's what is determining the range of the use that we are concerned with. You can develop polymer film capacitors that pretty much go over the whole range. So in terms of the frequency of use, we can have, even though it's the range of capacitance that is achievable is relatively small, not so high capacitances, but you can use it at over a whole range of frequencies. Mica, tending towards the higher frequencies. Then there's special low-loss ceramics and glasses. And then you have high permittivity ceramics. Okay. There are losses in these as frequency increases, but what is achievable, what kind of capacitance I want, and over what frequency range I am trying to operate it. Those are the two things we are looking at. Okay, let's look at the parallel plate capacitor equation, which we have seen earlier, and we come back time and time again. Simply that C is equal to epsilon naught epsilon R A by D. Now this epsilon R that we're talking about in this original equation that we've been using for a while, it's basically the value of epsilon R dash, what we had in the complex permittivity. The real part of it is what we're going to use in a calculation like this. If you remember, the double prime one in the complex was related to loss. So this is the one that is related to the actual values that we're going to use. And if I want large capacitances, it's obvious that there are three possibilities for large C, namely that I can have epsilon R large, what will be called our high K dielectrics. We'll look at that more in detail. Or we can have that A is large, or alternatively that D is small. And we will see later on what are the advantages and disadvantages of going in different directions, and why particularly for ICs, for chips, area can't be increased indefinitely. There's a problem there. We're trying to make them smaller. And what will happen if we make it thinner and thinner? We'll look at that shortly. So there is a whole area that I'd like to discuss that is related to these large or high K. K is another term that is used for epsilon, the permittivity, that's dielectric constant. So it's often known as high K dielectrics. We'll take that up shortly. Okay? These are some approaches we can take to get large capacitance. Make it very thin, make the area large, or choose materials that have got high dielectric constant. I'm going to take up the different kinds of construction for various types of ceramic, for various types of capacitors. Let's begin with a thin layer ceramic capacitor. I'm just going to look at 3-4 different kinds of capacitors. I'm sorry, ceramic capacitor. Okay? Now this comes in a couple of different variations. We'll look at the single layer model. And the essential construction is very simple. We have the ceramic. On both sides of it, there are contacts which allow us to connect the leads to it. And the whole thing is encased in some epoxy package. Okay? So that's the actual ceramic. These are the leads contact. And the whole thing is enclosed in an epoxy package. Typically a thermosetting epoxy is used. That means it will harden on heating up. It's a chemically bonded thing. And basically what the epoxy is doing is sealing off the capacitor from contact with moisture and dust. We saw some of the causes for breakdown and things like that were the environment, when there's too much moisture, dust, and things like that. And what the epoxy is doing is basically protecting this whole package from moisture and dust. Epoxy is a kind, you use it all the time. Give me an example. We use that in not Fevicol or Fevicol. Yeah, it's usually there. It's a kind of material, 2 parts. You mix it together. What do we call that? I mean, it is organic, but what is the common brand name? I'm drawing up. What is araldite type of stuff? You mix it, and after some time, chemically it just bonds, and that's one example of an epoxy. It's a type of material that has it's based on organics, and it hardens, and it's very rigid structure, typically. Here it's made by 2 parts. Some chemical is mixed together like you have for your araldite. And when it comes together, these 2 parts, it hardens. As long as these 2 are separate, it's a flowing kind of medium. But once the chemical reaction sets in, linking takes place and it hardens. When we come to polymer type of things in the next lecture, maybe you'll get a better idea of what is an epoxy there. So it protects it from moisture and dust, which we saw it'll increase the loss for the particular ceramic. Now, this is what is called the single layer capacitor. I can increase the total capacitance by connecting a bunch of these in series. And yet I want to do that to be as compact as possible. So the idea is, in a multi-layer capacitor, we are essentially doing the same thing as what we had for the single layer, except we have stacked it up. There are many layers, say n layers of the dielectric, and they're connected by electrodes. They're just stacked up. And so effectively they are like n parallel plate capacitors in series. All done in a very compact way. Basically we will have a series of what are called interdigitated electrodes. They're like fingers. Something like this. See, these are the metal electrodes, and in between is the dielectric that we have. So each of these sort of forms a pair between these two electrodes, any two pairs, we get a dielectric. So it's very compact, it's stacked, and then again the whole thing is encased within the package. And you have the connecting leads. So effectively, we've got n parallel plate capacitors. If each layer is d in thickness, then we find that the total thickness is actually going to be greater than nd, given that there are electrodes and things like that in between. So we will get some thickness of the whole device greater than nd. So we've got so much of capacitance, but all in the same area. Area has remained unchanged, just we've made the thickness larger. Area is a very critical thing in electronics. We don't have much area to play with. Up to about few hundred microfarads can be obtained by this approach. Then we can go to polymeric materials. Polymeric thin film capacitors. Now in this case, as we saw, we can go over a wider range of frequencies, unlike the ceramic case. In this case, the whole range practically of what I want is achievable. But we have that the dielectric constant is lower than for ceramics in general. Somewhere in the range of 2 to 3. Excuse me. But this remains constant, whatever be the low value, over the wide frequency range. And particularly losses, tan delta, which is my loss tangent, right, is low at high frequencies. So these are some of the advantages, in spite of relatively low dielectric constants, for the use of polymer thin film capacitors. Now, in order to get, because of this low value, in order to get sufficient capacitance, I must have a very large area. That means I must have very good design to be able to, and it should be compact, and yet I should have large area. That way, I can make it equivalent in capacitance, even though epsilon r is small. And the way this is done is basically to create a Swiss roll. You know what's a Swiss roll? You'll see it. Cakes that are made by putting some cream filling and then rolled up. Yeah? And you cut it into slices. Essentially, that's the design. There's going to be a Swiss roll design. That's the kind of approach that is used. There will be two polymeric sheets, let's say, and part of it on one side is metallized. So this is the polymer sheet, and on one side there is a metal electrode, say made of aluminum. Now we take another polymer sheet and we do the same thing, except that the metallization is on the opposite side. Okay, and these are very thin sheets. And then I take these two together. So this is also again the polymer part, and there is the metal part. When we put these two together like a sandwich, and then we simply roll it up. I'm drawing just a single line here, but imagine that each of these lines here consists of the stack, that sandwich. So I took, to illustrate, I took one sheet, I take another sheet, I put them together and simply roll it up. Okay? Now on one of these electrodes, or on one of these films, the electrode is on this side, on the other one, the electrode is on this side. So on both sides, I can put a metallic contact and get electrode connections to alternate layers of the film. So it's very much like the ceramic idea here. Where is it? Here, instead of it being like a solid stack, because of the fact that my polymer film is very thin, I can roll it up. So my rolled up, this is the Swiss roll, is now going to be given an end contact. Some kind of electrode contact is smeared over the end there. We could have some kind of conducting glue, okay, on both sides. So on this side, it will make contact with, say, this film. And on the other side also, we do the same thing by putting an end contact. It will make contact with this film. So alternate parts of it will get contacted. And then we attach the leads wires to it on both sides. Do you get it? It's like a little, very compact. It's now rolled up, very much like the ceramic idea there, except now it's so flexible, we can roll it up and get an equivalent capacitor. The next design is what are called electrolytic capacitors. And this is the approach we would take for getting large capacitances within a reasonable size. I want large values of capacitance. One thing I can do is to make it very big, but here I want the reasonable size too, and in that case the electrolytic capacitors are good. Excuse me. The first example we look at is the aluminum electrolytic capacitor. Essentially, it consists of an anode and a cathode, which are made of aluminum foil 50 to 100 microns thick. So thin foils of aluminum are used as the anode and the cathode. And they are separated by a porous paper which is soaked in some electrolyte. Liquid electrolyte. Okay. So the structure will look something like this. We've got on both sides the aluminum, two foils, and they're going to be separated in the middle by a paper, porous paper that is soaked in liquid electrolyte. But here on one side, the anode side, we find that we have an oxide layer that has been formed. Both the foils, their surfaces have been roughened. So this is also a roughened surface for this foil. But on this foil, we have the formation anodically of an oxide. Both these foils had been etched, so that increases the area. And what we have here is the porous paper filled with the electrolyte. This is what it will look like in cross section. Much like the polymer film, this is also created into a Swiss roll. Now here I don't need end contacts because the aluminum anode and cathode on either side serve as the end contacts. But these two things that are rolled together can be rolled up to create a structure like that. The whole thing is then is enclosed in a case. So some kind of a case will be there that covers this, and then you have the two wires coming out. So imagine that these two foils are taken with the porous paper in between and then rolled up to create this structure. The actual dielectric which is involved here is this oxide, Al2O3. A very thin layer, which is about 0.1 micron, is created anodically, anodic oxidation. So electrochemically, we have created the oxide on one of these foils. Both foils were etched to create the rough surface, but one of them, an oxide, was created anodically. And that is what is, because of this small thickness and large area, D is small, it's only about 0.1 micron, large area, all over the foil surface there is this oxide, we are getting the large capacitance. The anode is positively biased, as the name implies, and that means that the aluminum Al2O3 junction is reverse biased. Basically, the aluminum Al2O3 junction, this and this, is somewhat like a metal p-type semiconductor junction because of the nature of the Al2O3. And so if this is positive, that would mean that this junction is reverse biased, right? Because we have it almost like a metal p-type junction. So in that case, there is hardly any leakage currents. You're operating it more or less like reverse current. But if you switch the biasing, then you will get conduction through this capacitance, because now it will be as if the aluminum Al2O3 junction is forward biased. So as long as we operate in reverse biased mode with the aluminum Al2O3 junction, then we will not get any conduction through this capacitor. This is nice and can give you very large values of capacitance. The problem is that the liquid electrolyte, which is there in that porous paper, dries up. So after some time, it becomes useless. So the other approach to solve some of this problem is to use a solid electrolyte, tantalum capacitor. Tantalum is another material that can work here. We're going to replace the liquid electrolyte by a solid electrolyte. Essentially, the anode consists, let me give a sketch of what this device will look like. There is a pellet, tantalum pellet, which is porous. And it is created by a process called sintering, compacting it and keeping it at a very high temperature where it will densify. So that's the tantalum pellet. And then we have around it, I'll show the cross section in a second. Let me just draw this. There's silver paint, and then some leads that come out of it. And the whole thing is enclosed again within a package. I'll show this cross section here. There's silver paint, and this is the tantalum pellet. And what we'll do is we'll look at a part of this, say one area here. I'm going to expand that to see what it looks like in cross-section. When we look at that area, it looks very similar to the case of the liquid electrolyte cell, except that instead of two aluminum foils, what we have now is that we have the tantalum pellet, okay, the inner part of it. Well, let's say what I'm drawing here actually will be more like this area. Okay, this side. So the tantalum is on the inside. It doesn't matter one way or the other. I'll just have to reverse the diagram. And you also have a similar tantalum oxide layer that has been created, much like we did for aluminum. Ta2O5, tantalum pentoxide. Then we have a solid electrolyte, which in this case is MnO2. Manganese dioxide, which is the solid electrolyte. On top of that, then, there is a layer of graphite. Graphite is conducting, to which then silver paste is coated. So tantalum pellet, a big pellet, surface has been oxidized to give us Ta2O5 by anodic oxidation. On top of that, we put a paste of MnO2, then graphite, and then silver paste. So this whole thing is again, this one tantalum pellet, and this whole layer here consists of 2-3 layers. I haven't shown it. What we have just shown is one layer there, silver paint, is really consisting of smaller layers which have been blown up here. The real dielectric medium in this case is Ta2O5 again, with a dielectric constant of roughly 28. Okay? And the outermost packaging that we use here is also some kind of resin, organic resin. So it's encased again to protect it from moisture and dust. There's advantages to this. I'll just simply list the advantages. Small size, increased temperature stability, it's also stable over long periods of time, which is the disadvantage that the liquid electrolyte had, that with time as the liquid electrolyte dries up, the capacitor is not going to function properly. But so this is much more stable in terms of time, and therefore it leads to high reliability. So the solid electrolyte tantalum capacitors have these advantages. I'll introduce a few terms now before we go to high K dielectrics. I'd like to make some comparisons between dielectrics, capacitor materials. And when we do that, we need a few terms, not simply the total capacitance. Now that will depend on the size of the device, but I've got to have a better way of comparing the different materials. If I simply say this gives me a larger capacitance, well, if I take another material and make it large enough, the area is large enough, I can get an equivalent capacitance. So how do we compare capacitor materials? And for that, I'll introduce a few terms. We define a term called capacitance per unit volume. That's sort of like a capacitance density. You know, we've made within a given volume, what is the capacitance? Namely, C volume is equal to capacitance by A times D, where again we're using the idea of a parallel plate capacitor. Area times thickness is the volume. Now, if you recollect, what was capacitance? Epsilon R, epsilon naught A by D. And we're going to again divide that by AD, which leaves me with the capacitance per unit volume is equal to epsilon R, epsilon naught by D squared. So what it tells me is that one approach is to get large high K dielectrics, to get large capacitance. The other is, because of this D squared term, small d's, in which case I can get large capacitances. And so the thickness becomes very important. Let's consider a couple of examples. The dielectric constant of mica, for example, is greater than that of many polymers. Yet, because the thickness of mica is also greater than the thickness of polymers, polymers can be made as very thin films, the advantage that mica has in terms of dielectric constant is more than offset by the disadvantage it has in being thicker, and therefore the volume, the capacitance per unit volume of mica is less than that of polymers. Another example is that of aluminum capacitors. In this case, we find that the capacitance per unit volume is very large. And the question would be why? If you remember, the way this works is that there's a very thin layer of oxide. And that's the real dielectric. 0.1 microns or something I said. So when you have the thickness of the Al2O3 layer is very small, you're correspondingly going to have a larger capacitance per unit volume. But because of the very thinness of that layer, it is possible that you're going to have local breakdown. That's not exactly a very uniform layer. And then you're going to apply this field, and it's so thin, so the fields are going to be very high across it. So local breakdown may occur. The beauty is that the electrolyte that is chosen is such an electrolyte that through some electrolytic reactions, it heals the breakdown. So where the Al2O3 layer, which is the dielectric, breaks down due to the high fields locally, the electrolyte that is used by electrolytic reactions heals that breakdown, that local breakdown that is there. And we will see for different materials, different properties. We'll compare in a second. Ceramics in particular have C volume greater than that for polymers in general. Either due to their high, as we saw for mica, it's got a high value of the dielectric constant, or D is small. For various, either of these two reasons, say in the aluminum capacitor, D is small. In other cases, epsilon r is large. So either way, most ceramic capacitors will give you much higher capacitance per unit volume. Another important point that we need to look at is what is the operational voltage that the capacitor material can sustain, or working voltage. We know that as D, I think I've got my papers all flipped around here. As D decreases, the capacitance per unit volume is increasing. We know that. We just saw the relationship, D squared, 1 by D squared. But as D decreases also, if you remember earlier, the working voltage will decrease. You're going to get breakdown eventually. The thinner it gets, the higher the field, so eventually you're going to get breakdown. So you can't apply larger and larger voltages across it. And we saw this earlier in terms of the breakdown field, breakdown strength. And breakdown strength, we saw, depends on numerous factors. So I can't just look at the breakdown strength, some value, to determine what should be the operational voltage. Under different circumstances, the breakdown field strength, something as simple as there's dust on it, theoretically it should be able to sustain a greater field, but because of dust it got shorted out and broke down. I want to operate within a safe limit. So what I'll do is that even though I know that I can sustain intrinsically a higher value of voltage, my working voltage will be chosen to be lower than what is the maximum voltage that can be sustained. Okay? So working voltage will be lower than the maximum voltage related to this EBR term, EBRD. So we use a safety factor, which I label as eta. So it's going to be a few times less, say two times less, or 1.5 less than the maximum voltage, what we'll operate at. Let's say that the maximum voltage is Vmax, which is related to our breakdown field strength times the thickness. That's the maximum voltage as dictated by the breakdown field. But the maximum safe operating voltage is then given by Vmax by that safety factor. I'm derating it, we say, once, twice. So this can be written then as equal to the breakdown field strength D by eta, where eta is greater than 1. That's where you get a lower voltage than the than the maximum voltage. There's another term also, the maximum energy that can be stored per unit volume. Which is given by E vol. This is the maximum energy that can be stored per unit volume. It's equal to half C V max squared. Okay, I've got my Vm there, and then divided by the volume. Half CV squared is your energy, and then divided by volume. So if we make substitutions here, we'll get half. For C, we are going to substitute as epsilon r dash A by D. And then we are going to substitute for Vm or Vmax. No, sorry, Vm is the safe operating voltage, not the max. That is, this is Vm, not Vmax. So for Vm squared, we'll get the breakdown field strength times D by eta, the whole squared, times 1 by AD. Substituting for the safe operating voltage, maximum value, the capacitance, and then per unit volume, which simplifies then to epsilon naught, epsilon r dash by 2 eta squared, the square of the breakdown field strength. So we see that both this term and this term influence the ability of the capacitor to store charge. I can't simply look, does it have a very high dielectric constant? If it has got low breakdown field, then I will not be able to store compactly the charge. So both these terms influence the ability to store energy. Here's one more term that we will use, is the rate of dielectric loss per unit volume. At Vm. And we will use the term W subscript vol, which is the power loss per unit volume, is equal to, we have seen this equation that we had earlier for the power loss. Long back, in one of my earlier lectures I gave this, if you go back. Br squared omega epsilon naught epsilon r dash tan delta, except that now we are dealing with a maximum safe operating voltage, and so the EBR squared by eta squared term comes instead of plain EBR squared. So this is the loss per unit volume at Vm. So if tan delta is high, dielectric loss is also high. We saw this earlier. In ordinary ceramics, there's a lower losses, and so they are more efficient at storing energy. The so-called high K dielectrics have other advantages, but they have got higher losses. Then among the ceramics, there's something called, among the polymers, there's something called polystyrene. It has also got low tan delta. We'll see in a second why. And so that also leads to low losses. So these are different terms that we can use to compare. Not only simply the permittivity and the tan delta, but there's many other terms that we can use to compare the different materials. I don't have time to go into details much about it, but if we take just a couple of examples and compare for a polymer film and let's say for a high K dielectric. This polymer is say polystyrene, the one we just mentioned. And we're going to compare different properties. Permittivity, low permittivity, high K dielectric maybe something like 1800. This is something, say, that's based on barium titanate. Tan delta losses, very low in the case of this polystyrene, relatively high in this high K dielectric. Breakdown field strength in terms of kilovolt per centimeter, 200 to 250, it's about 100 there. Typical thicknesses, 1 to 2 microns in the case of high Ks. For particular applications, it could be, it's going to be much less in certain applications, but somewhere like this may be a comparable value. Now the C wall, capacitance per unit volume in terms of microfarads per centimeter cube, 22.1, and here we see the big difference, 159.4. Charge storage capacity per unit volume. The energy that is stored per unit volume, millijoules per centimeter cube, 1.1 and 200. The ability to store charge in a very compact area is there. The loss, on the other hand, here is 0.00025 units of watts per centimeter cube. Here it is 7.5. Okay? So big difference in loss, but depending on the applications, we'll choose one or the other. This is primarily the mechanism of polarization is electronic bond polarization. Here, we have seen in the case of barium titanol large changes in the positive sublattice and negative sublattice as it shifts around. So that's the big difference. Here there's large changes of ionic sites that are moving, whereas here it's just electronic bonds that are getting polarized, and that is why we find these significant differences. I wanted to deal with the temperature coefficient. I think that's all I'll do. I don't think I have time to go into the high K dielectrics, so let's just do this and finish up. The temperature stability also of dielectrics. Obviously, the temperature stability will depend on the temperature dependence of the permittivity and the temperature dependence of tan delta. How these are behaving with temperature is what will affect the temperature stability of the dielectric as a whole. There are different ways of looking at it. Say, for example, in polyethylene terephthalate, which is normally called PET. You know, the PET jars and things like that, the plastic, it's a plastic. We see that it's a polar polymer, so there are dipoles, but at room temperature, even when you apply a field, we do not get, it's not easy for it to move within that. So if we apply under AC conditions, it's not able to move around very easily. But as we heat it up, the polymer becomes soft. And when the polymer becomes soft, the dipoles that exist, it's a polar material, are now within that softened material able to respond much better to the applied frequency. So with increasing temperature, we see that it is able to function to higher frequencies, because now in the softer matrix, it is able to flip around more easily. The non-polar ones will behave very differently. So we've got, in this case, both for permittivity and tan delta, strong temperature dependence. On the other hand, for non-polar cases, some kind of non-polar polymer, say the one that we looked at earlier, polystyrene, it's relatively flat. It's electronic bond polarization, I said. So epsilon r dash and tan delta don't change, relatively insensitive to temperature. Okay, so different materials have got different temperature dependencies depending on why they are getting polarized and so on. We will define a term called the temperature coefficient of capacitance, or TCC. Basically, the definition is the change in capacitance, delta C, or the fractional change in capacitance, so delta C by C, per unit change in temperature. That is, what is this? TCC. The fractional change in capacitance, delta C by C, per unit change in temperature, which can be written as 1 by C delta C by delta T. And remember that C here is epsilon A and D. In this term, what all is temperature dependent? Everything. Permittivity is also temperature dependent. A and D, which are related to the thermal expansion of the material, are also temperature dependent parameters. So we'll see that different materials will have different behavior depending on its influence on the both the coefficient of thermal expansion as well as on the effect on epsilon r. Let's consider a parallel plate capacitor. Okay, with dimensions x, y, and z, where z is the thickness, and x and y constitute the area of that parallel plate capacitor. So we will write that C is equal to epsilon r, epsilon naught, xy by z, simply writing area as xy and thickness as z. And we want TCC, which is equal to 1 by C dC by dt. It's very easy for you to go through this. There are four terms that we can differentiate with respect to temperature. Epsilon r, x, y, and z. So if we take the differential of all this, we will end up with something like this, that the TCC, I'm not going to go into it simply for lack of time, but you can show it. It's too simple. Plus 1 by x dx by dt plus 1 by y dy by dt minus 1 by z dz by dt, because of the z being in the denominator there. Now we define that lambda, which is the thermal coefficient of expansion, is 1 by L dL by dt, where L is any dimension. So essentially what lambda, which is the thermal coefficient of expansion, TCE, tells us is that 1 by x dx by dt or 1 by y dy by dt or 1 by z. Given that this material is isotropic, which means it has properties the same in every direction, we can then write 1 by x dx by dt is equal to 1 by y dy by dt is equal to 1 by z dz by dt. If that is the case, then I can simply cancel any two of these because we are subtracting one from the other, right? And I'm left then with TCC equal to 1 by epsilon r d epsilon r by dt plus x or y, 1 by x dx by dt or 1 by y, whatever we take, we will simply write it as 1 by L dL by dt. Or in another form, 1 by epsilon r d epsilon r by dt plus lambda, which is the TCE. So thermal coefficient of capacitance is equal to 1 by epsilon r d epsilon r by dt plus the thermal coefficient of capacitance. I'd wanted to go a little bit more in dealing with some fairly recent, interesting, advanced topic of high K dielectrics, but I don't have the time for that because I really want to cover in 2 more lectures polymers. Okay, so we'll take up that next. I meant to do polymers today, but I discovered we have an extra lecture, so I thought we'll just complete this because it's useful information. Okay, we'll stop here, and then we've got two more classes left.